Thank you everyone for attending this talk. Today I will be talking about tight harness results for training Depth-2 ReLU networks. And this is joint work with Subhi, Goel, Adam Klivans, and Daniel Reichman. Let us start by recalling the definition of neural networks. Neural networks take in inputs. Here we denote them by x1 and x2, so on and so forth to xn. Each of them is a real number. Sometimes we also write x to denote the vector x1, x2, so on to xn for brevity. A neural network can have multiple layers, and each layer can have multiple nodes. Each node can have an edge to each of the nodes from the previous layer. For example, the node shown here has an edge from each of the input nodes. Associated with each edge is a weight. Here we denote it by Wi, which is a real number. The input to the node is the weighted average of the input. Specifically, the input to this node shown here would be W1x1 plus W2x2, so on and so forth, plus Wnxn. This input is passed through the activation function of the node. We will be more specific about the activation function in a moment, but for now you can think of it as some function from real numbers to real numbers. This activation function gives the output to the node. And as I said earlier, there can be multiple nodes in each layer, which give us multiple outputs from that layer. These outputs can then be used as input to the next layer, and we can build multiple layers on top of each other. Now, in many of the recent breakthrough practical results of neural network, the neural networks that I use have many layers and hence the name deep learning. However, from the theoretical perspective, even relatively simple and shallow neural networks are still not completely understood. And thus, in this work, we focus on a pretty simple class of neural networks, which is the class of Depth-2 fully connected neural networks. This means that there are only two layers on top of the input layer. And furthermore, each node has an edge from all of the nodes from the previous layer. And moreover, the final output layer only has one node, meaning that the output is just a real number. Now, as the title of this talk suggests, we also limit ourselves only to ReLU activation function. So the ReLU activation is a function that takes in some real number c and output the maximum between c and 0. And for brevity here, we will write this function as bracket c subscript plus. Now, the top layer that we are considering here is using the identity activation function, which just means that it outputs exactly the input, which is the weighted sum from the previous layer. Throughout this talk, we use k to denote the number of nodes in the middle layer, and we use w superscript j to denote the weight vector of the edges coming into the jth node in this layer. For the node at the top, we use a1, a2, and so on to ak to denote the weights of the edges coming into it. With this notion in mind, such a neural network can be viewed as a function that takes in an n-dimensional vector x and output the sum of I from 1 to k of ai times the ReLU of wi dot x. We call a class of such neural networks or such functions as k-ReLU. It's worth noting here that the weights at the top, a1, a2 to ak, can be assumed without loss of generality to be either +1 or -1. The reason is that the scales of these weights can be pushed down to the wi's instead. Now, in this work, we are interested in the problem of training or learning such k-ReLU networks. Let us start with the former problem, the training problem. In this problem, we are given a set S of samples, X and the label Y, And our goal is to find a k-ReLU that fit these samples as well as possible. Specifically, we want it so that if we pass x through to our network, the output should be as close to y as possible. More formally, we would like to find a k-ReLU f that minimizes the loss function between the output of the k-ReLU on x and the given label y for some loss function. And recall here that our unknowns are the weights a1 to ak and w1 to wk. In this work, we only consider one loss function, which is the square loss, which is a pretty popular loss function. This just take the difference between the two numbers and square them. There are two cases that we will be discussing regarding these problems. The first one is the realizable case. So this is the case where there is a promise that some unknown k-ReLU achieves zero error, meaning that its output is exactly equals to y always. And another case is the agnostic case, where this statement is not true. So even the best k-ReLU doesn't achieve zero error. So that's the training problem. Now, we also consider the learning problem, which is almost the same as the training problem, except that there is now an unknown distribution D, and our samples are drawn independently at random from this distribution D, and the loss is now with respect to the underlying distribution D instead of the given samples. Now, for those of you who are familiar with learning theory, we are only considering proper learning here, meaning that the function that we would like as an output is only allowed to be a k-ReLU. So you cannot output an arbitrary function. Notice here that the learning problem is harder than the training problem. Specifically, if you set the distribution D to be the uniform distribution on S, then you can take any learning algorithm and turn it into a training algorithm as well. What this means is that for the purpose of giving an algorithm, it suffices to only give an algorithm for the learning problem, whereas for the purpose of giving a hardness result, it suffices to only prove hardness for the training problem. Finally, before we state our results, since our result will be quantitative on the additive error as well, we will need some normalizing assumption. Specifically, we will assume that each wi has norm at most 1, and the input vector x also has norm at most 1. And these two implies that the output y's are between minus k and k. So with that in mind, we can now state our results, which can be divided into 3 groups. First is NP-Hardness results, second is algorithms, and third is tight running time lower bounds. Our first result is that even training a single ReLU is already NP-hard, and in fact, even minimizing the loss is NP-hard to approximate to within an almost polynomial in n factor. And note here that this NP-hardness only holds in the agnostic setting, and this is not a coincidence, because if we are in the realizable setting, then the problem of training a single ReLU can be formulated as a linear program, which of course can be solved efficiently. On the other hand, even if we are in the realizable setting, if there are multiple ReLUs, we show that this is NP-hard. Specifically, for any constant k greater than or equals to 2, we show that training k-ReLU is NP-hard even in the realizable case. I would like to note here that there are quite a few independent and parallel works that prove results similar to us here. Specifically, they et al. Also show that training a single ReLU is NP-hard. Bakshi et al. Also show that training 2 ReLU is NP-hard, although they did not show that training k-ReLU is NP-hard for k greater than or equals to 3. And finally, Boop et al. Show NP-hardness of training for an architecture that is slightly different than us. Specifically, they consider one where the top node is also a ReLU node and not an identity or additive node as we are using here. Now, our NP-Hardness results show us that even when there is one, two, or only a few ReLU nodes, the problem of minimizing the loss is already hard for multiplicative approximation. However, we can show that for additive approximation, we can get quite good algorithms. First, we show that in the agnostic setting, there is an algorithm for learning k-ReLU to within an additive error of epsilon that runs in times exponential in k to the fifth over epsilon square times polynomial in n and k. When it's realizable case, this running time can be sped up further. Specifically, the exponent goes down from k fifth over epsilon square to roughly k cubed over epsilon. It is interesting here that the realizable case seems to be easier than the agnostic case, since our algorithm for the former is faster than the latter. And hence it's natural to ask whether this difference is intrinsic or whether we should be able to come up with faster algorithms for agnostic learning. It turns out that we can show that this difference is intrinsic. Specifically, we can show tight running time lower bound for both agnostic and realizable setting with respect to epsilon. To state our running time lower bounds, we have to first recall some complexity theoretic hypotheses. The first is the exponential time hypothesis, or ETH, which states that no 2 to the little of n time algorithm can solve the 3-SAT problem, where n denotes the number of variables. In other words, this is asserting that the brute force 2 to the n time algorithm that just goes through each of the assignment and check whether it's satisfiable is optimal up to the constant in the exponent. We'll also be using a strengthening of ETH called gap ETH, which states that no 2 to the little of n time algorithm can distinguish between a fully satisfiable 3-SAT instant and one which is not only not satisfiable, but not even 0.99 satisfiable, meaning that every assignment violates at least 1% of the clauses. So under the gap exponential time hypothesis, we can show that for any constant k greater than or equals to 2, the training k-ReLU problem cannot be solved in times exponential in little of 1 over epsilon times poly in n k, where again epsilon is the additive error. Note here that in terms of epsilon, this matches with the algorithm that we give in the realizable case, but it remains an interesting open question to determine the exact dependency of the k. Alright, so that's the realizable setting. Let us now move on to the agnostic setting. For the agnostic running time lower bound, we will need a different and new complexity theoretic hypothesis. To state it, let us recall the densest k subgraph, or DKS problem, where we are given an undirected graph G on n vertices and a positive integer k, and the goal is to find k vertex subgraph of G with maximum number of edges. Our hypothesis, which we call gap ETH for densest k subgraph, or gap ETH for DKS, states that no 2 to the little of n time algorithm can approximate densest k subgraph to within a constant factor. Now, honestly, this is a very strong hypothesis, but it also seems somewhat plausible. And one reason is that if you assume that certain random CSPs are hard to refute in sub-exponential time, then the gap ETH for DKS would follow. On the other hand, the bad news is that no NP-Hardness of approximation for DKS is known, even for say 1.1 factor. So it seems very hard to prove and possibly out of reach of the current techniques. Okay, so using this admittedly strong assumption of gap ETH for DKS, we can show that even for agnostic training of one ReLU with additive error epsilon, it cannot be done in time exponential in little o of 1 over epsilon square times poly nk. Now 1 over epsilon square here in the exponent is tight because it matches with our algorithm. And moreover, this gives us separation between agnostic and realizable learning, because in the latter we can get it in exponential in 1 over epsilon if k is constant. So those are all our results. For the rest of this talk, I will go through each of them and describe at a high level how it's proved. We will start with the algorithms. So I copy the results here on the right, and I also copy the definition of k-ReLU here on the left. So we'll be using a simple but very nice training algorithm of Aurora et al., which works as follows. For each input sample xy, we guess the signs of w1.x and so on and so forth to wk.x. Furthermore, we also guess the a1, so on and so forth to ak. And recall here that each ai we can assume to be in plus minus 1. And finally, the observation here is that once we guess the signs and also the AIs, each sign corresponds to just one additional linear constraint. And after this guessing, the fx is just a linear combination of x without the ReLU function anymore. So now we can formulate our problem as a convex program and solve it efficiently. Now, in terms of the number of guesses, since we have to guess k signs for each sample, we will have to guess roughly k times m signs, where m denotes the number of samples. So this means that the running time of our algorithm is exponential in k times m and times the polynomial in the problem size. So at a glance, this might be a not very good algorithm because the running time depends exponentially in the number of samples. But it turns out that this is not an issue. And what comes in to help us here is generalization bounds. For those of you who haven't seen generalization bounds before, generalization bounds just say that when you solve a learning problem, you only have to sample a certain number of samples and train them well, and then you immediately get also a low error for the underlying distribution. And specifically for the agnostic case, it follows from the work of Bartlett and Mendelssohn that k to the fourth over epsilon square samples suffices. So plugging in m equals to this number into our running time on the left, we immediately get our agnostic algorithm. For the realizable case, it's known that the number of samples required can be improved. Specifically, Tribo et al. Show that only k square over epsilon samples suffice. So plugging in this bound, we immediately get the improved running time lower bound for the realizable case. So that's it. That's the entire proof of our algorithms. Now let us move on to the NP-Hardness results. So I copy the results here on the left for both the agnostic and realizable cases. Let us start with the agnostic case. So here recall that we are going to prove that training a single ReLU is NP-hard. And let me copy the single ReLU here, which is just a1 times w1.x passed through a ReLU. And notice here that since a1 can be only plus minus 1 and there is only a single a1, we can assume with our law of generality that it's just 1. And for convenience, we will write w1 as just w since there is only one vector w. So our NP-Hardness reductions will start from the set cover problem. Recall that in set cover, there is a universe which I denote by M, and there are subsets T1, T2, and so on to Tn of M. And our goal is to find the smallest number of subsets whose union is the entire universe M. To reduce this problem to the training a single ReLU, we set the dimension of the input to the ReLU, small n, to be equals to the big N, which is the number of subset in the set cover, and we view each subset as a coordinate. Now, before we describe the reduction, let us note here that the intended solution here would be to set a coordinate I to 1 if and only if Ti belongs to the optimal set cover. And if it doesn't belong to the optimal set cover, then the coordinate will be set to 0. So with that in mind, let us continue with the construction of the samples. And the easiest way to describe this is to view each sample xy as a constraint that ReLU of w.x is equals to y. There are two types of constraints we'll be adding here. The first is the element constraint. Specifically for each element j, we create many copies of the following form. The ReLU of 1 minus sum of wi over all I such that Ti contains j is equals to 0. The point about this constraint is that in the intended solution, since we set all coordinate I for which Ti belongs to the set cover to be 1, we have ensured that in this sum, at least one of the term is 1. So the left hand side will be 0, and this constraint will always be satisfied in the intended solution. The second type of constraints that we'll be adding are the subset constraints. So for each subset Ti, we will create a constraint that ReLU of delta minus wi is equals to delta, where delta is some small positive real number. The point here is that this constraint is satisfied only when wi is less than or equals to 0. In other words, it is violated when Ti is selected in the set cover. Now, due to time constraint, we will not be going through the entire proof here, but the rough idea is that the element constraint ensures that the selected set is a valid set cover, whereas the subset constraint ensures that we are picking as few sets as possible, and hence this is indeed the set cover problem. Alright, so that's conclude the high-level overview of the reduction and the proof that training a single ReLU is NP-hard in the agnostic case. Before we go forward, let me note here that this proof doesn't directly give the hardness of approximation to within almost polynomial factor yet, and the reason is that set cover itself can be approximate within log m factor. So to get the claimed hardness of approximation, we have to reduce from a different problem, which is a generalization of the set cover problem called the minimum monotone circuit satisfiability. This problem is known to be hard to approximate to almost polynomial factor, and by generalizing this reduction, we can prove a similar statement for the agnostic training of a single ReLU. Alright, so now that we are done with the agnostic case, let us now move on to the realizable case. And I'm copying the definition of K-ReLU here for convenience. It turns out that in this case, Wu had already proved an NP-hardness for training K-ReLU in the realizable case where K is greater than or equals to 2 before, except that his proof only works when we assume that A1 and A2 and so on to AK are all equals to 1. Thus, the only thing we have to do is to handle the case where A1 and so on to AK can be negative. And to do this, we use a new gadget, which is just a set of points, such that these points can only be realizable by K-ReLU with A1 and so on to AK being all equal to 1. And by adding these points to the reduction of Wu, we immediately translate his result to the case where all the A's may not just be plus 1. We have completed our discussion on the NP-hardness results. Let us now move on to the last group of results, the time running time lower bounds. We can start here with the realizable case. Fortunately for us, our NP-Hardness reduction that we just discussed, together with the known hardness of approximating K coloring of page rank, already imply a lower bound of exponential of little of 1 over epsilon for the case of realizable setting under the gap ETH assumption. So we are done here. Unfortunately, the agnostic case is not as simple. Specifically, our set cover reduction only give a lower bound of exponential of 1 over epsilon instead of 1 over epsilon square that we want. And this is not a coincidence. In fact, whenever the intended solution is almost correct, then there is actually an algorithm with running time exponential in 1 over epsilon instead of 1 over epsilon square. And I will not be too specific here about what it means to be almost correct, but you can think of it as having a very, very small loss. So from this, what can we conclude? If we want to prove a lower bound of 1 over epsilon square, then even our intended solution cannot be almost correct. We will now describe our reduction from densest case subgraph that satisfies this property. So we view each vertex as a coordinate, and the intended solution is to set a coordinate to 1 over square root k, even only if the corresponding vertex belongs to the optimal subgraph. Note that since the subgraph contains k vertices, the intended solution has norm 1 as desired. In terms of the samples, once again we can describe them as constraints. The first type of constraint is cardinality constraints. For each vertex j, we create the constraint ReLU of wj minus 0.5 over square root k equals to 1. Now note here that since most of the w are very small compared to 1, this constraint will mostly be violated even in the intended solution. And this indeed aligns with our intuition earlier that even the intended solution cannot be almost correct. Furthermore, among all weight vectors w of norm 1, the loss with respect to the cardinality constraints is minimized exactly when k coordinates are set to 1 over square root k. In other words, these cardinality constraints are incentivizing us to pick k vertices and not more. The second type of constraint is the edge constraint. For every edge ij, we create the following sample. So ReLU of wi plus wj minus 0.75 over square root k is equals to 1. Now note here that unless both vertices I and j are selected in our subgraph, the left hand side will evaluate to 0. But if both of them are selected, then the left hand side will evaluate to a non-zero number. In the latter case, we will be incurring smaller loss. In other words, these edge constraints are incentivizing us to pick vertices that induce a lot of edges. I will not have time to go into more detail here, but this reduction indeed gives us the exponential of 1 over epsilon square running time lower bound for the agnostic case as desired. Alright, so that's all the technical stuff that I will talk about today. Let me now conclude. In this work, we study the problem of training and learning Depth-2 ReLU networks, and we give simple learning algorithms and NP-Hardness results and matching running time lower bound. Despite of our results, there are still several interesting open questions and research directions. A concrete one is to obtain a tight running time lower bounds in terms of k. Recall that our running time lower bound is tight in terms of epsilon, but we do not know what should be the right dependency in terms of k, and it would be nice to figure this out. Another is to consider other loss functions. In this work, we only focus our study on the square loss, but there are other loss that are used in practice and in theory as well, such as absolute loss function or the cross entropy. So our NP-Hardness result, especially for the realizable setting, extend to this loss function. However, it is unclear whether we can get tight running time lower bounds there as well, and it would be nice to understand these questions. Another interesting question here is to consider deeper neural networks. As I stated at the beginning of the talk, most of the neural networks used in practice are pretty deep, much deeper than 2 layers. So it would be interesting to prove hardness for deep networks. In fact, we are not aware of any hardness result even for Depth-3 ReLU networks. Next, it would be nice to relax the assumption that we use for proving the tight running time lower bound for the agnostic case. Specifically, currently we use the gap ETH for densest case subgraph assumption. So it would be nice to prove it under a more believable assumption, such as the gap ETH or the ETH itself. Finally, it would also be interesting to consider the improper learning setting. Recall that in improper learning, we can output any function that doesn't have to be a k-ReLU. And in this setting, Goel and others show that there is a faster algorithm that beats even the running time lower bound in the proper setting in our work. So what this means is that improper learning probably give you more power in this setting, and it would be nice to prove a matching running time lower bound there as well. And with that, thank you all very much for your attention.